Welcome back everyone to another Organic Chemistry 2 topic video. My name is Shoaib Arab, and today we will start with Chapter 22 of Organic Chemistry by Wade. Chapter 22 mainly deals with condensation and alpha substitutions of carbonyl compounds. But before we jump into this, we need to go over some naming conventions related to carbonyl compounds. So let's look at this compound over here. We have our functional carbonyl group right here. And now we can distinguish each carbon after your functional group based off of its distance from your carbonyl. So the first carbon over from your carbonyl compound is known as the alpha carbon. If we were to go 2 carbons over, these carbons are known as beta carbons. And if we were to go a 3rd carbon over, these carbons are known as gamma carbons. And this can continue so on and so forth down the entire Greek alphabet. Now it's important to realize which carbons you're dealing with because the alpha, beta, and gamma and other carbons have unique properties based off of their proximity to the carbonyl compound. But for this video, we're going to focus mainly on the alpha carbon. So let's look at another example. Let's redraw that. The alpha carbon is special because when you deprotonate the alpha carbon, it actually has a resonance structure that goes between the carbon and your carbonyl compound. So if I were to deprotonate and remove this hydrogen, these electrons would go back to your alpha carbon. And as an intermediate, you would get R, C double bond O, C minus R, H. Now I can resonate the negative charge on the carbon with your carbonyl compound. If I were to move the negative charge down and make a double bond here, the double bond between your carbonyl would go up to the oxygen. And so I get a resonance structure that looks like this. This resonance form between the double bonded carbon and the carbonyl is known as an enolate ion. The enolate ion is special in that we're able to create a negatively charged carbon that is relatively stable due to its resonance with the carbonyl compound. Now this opens up a wide variety of reactions because a negative carbon is a pretty strong nucleophile, and we can use it to attack electrophiles. So let's look at an example. Let's say we started with this enolate ion, and we were to react it with this ketone group. Now, if you remember Grignard's reagent, the same type of mechanism will occur here. Your negatively charged carbon will come and attack the carbon of your other carbonyl compound. Because this carbon right here is partially positive, while the oxygen here is partially negative. When that attack occurs, your double bond will break and those electrons will go up to the oxygen. So as an intermediate, you would get this. Where this group right here is the electrophile that we just attacked. And if you leave this in solution long enough, Eventually, your oxygen will protonate, and your final product will look like this. C double bond O, C, R, H, just give me this arrow, C, O, H, and 2 groups. This type of reaction is known as the addition of an enolate to a ketone, or it can be done with an aldehyde as well. And this is a type of alpha condensation reaction. So in alpha condensation reactions, we are using the alpha carbon in the enolate ion form to attack other carbonyl compounds. This alpha condensation can also occur with ester groups. So let's say we just start with the same enolate ion. This time, let's attack an ester group. The initial mechanism is the same, in that the negatively charged carbon will nucleophilically attack the partial positive carbon of your ester group. So this negative charge will attack this carbon, and your double bond breaks, and oxygen takes the lone pair. So as an intermediate, you would get now here, instead of just waiting for the O minus to get protonated by water, what would actually happen is your negative charge would come back down to form the double bond again. And as it does that, it's going to kick the ether group off. So we're going to break the ester into a ketone. Your final product would look like this. Plus OR minus. So this mechanism was a little different in that we clearly preserved the carbonyl at the end. However, we broke the ester group into 2 different parts. This motif of reaction will come up a lot in chapter 22 because that negatively charged carbon of your enolate ion is extremely nucleophilic and can initiate a lot of similar reactions. So as we move on in the rest of this chapter, we're going to repeatedly see how the enolate ion plays a key role in alpha condensations and other carbon-carbon reactions.